Yeah, yes, please tell me.
Is it that we somehow manually also try to find out the key points, or it is through algorithm only that it gives us the key points?
Um, so in our course, what we are trying to do is we are just trying to mimic how we find how we look at key points when we are looking at algorithms. But at the end of the day, you would be using an algorithm only. So our objective is to come up with an algorithm that does a pretty good job based on or at least satisfying the properties that we have been thinking about.
So in this particular Harris corner detection, as the name goes by,
Mm.
should we decipher that it'll give only a corner, but
No,
key
no,
points can be more than the corners, the
that's
text
right.
application
So
also.
it is, so if you just look at the paper name, it has a combined corner and edge detector. They call it as a corner, but as such, it has nothing specific for corners. You could consider it as a key point. It's more like a loosely used word. You have a
Okay.
point there. Corner is not exactly, see, your usual definition of a corner could be a junction of two edges. That's what we mean by a corner, is it not? Here it is not in that strict sense. Here it is in the sense that it's a key point having certain features.
Okay.
Good. So any other questions? Okay, we will start. Then maybe let others watch it later. So I again request all of you to have the pen and paper with you. This, whatever we are going to now discuss about the Harris Corner detection, demands your utmost attention. Okay, so keep everything away for an hour and see it. Otherwise you will take a lot of time later to decipher certain things and understand certain intricacies of this Harris Corner detector. So yeah, tighten your seat belts and give me your full attention here. In the previous class, we started looking at into what are the desirable properties for key points or feature points, or you call it as corner points, whatever you call it. These are the names that we use interchangeably. So first property, important property that we have seen is repeatability. By that, what we mean is, let's say you have given an image and your algorithm has computed some important key points there. Now let's say you have given as an input to your algorithm another image which might be having a slightly different viewpoint, or having maybe, let's say, around 80 to 90% of overlap compared to the original image, or there could be an illumination change here compared to the earlier image. But still, whatever key points in the regions that are common to both images, whichever key points that were detected earlier by your algorithm in the first image, the same algorithm when run on the second image in that common region, it should give you again the same key points. That's what we mean by repeatability. Then we talked about reliability. By that, what we meant is, you should not there should not be any ambiguity on to which key point in the other image the key point in the first image would map to. So it should be very reliable. Third, we discussed about is compactness. By that we mean that we should be able to efficiently represent a given image with reasonably good, less number of key points. Let's say you have 256 by 256 image. Assume that if you are having, let's say, a ballpark number I could throw is, let's say if you have a 300 key points, let's say, should be enough to represent your image. Your key, every pixel should not be a key point at the end of the day. So that's what we mean by compactness. The fourth property we have discussed is how you represent the key point. So essentially, one simple way you could represent is take a patch around it that's representing it. We'll come back to how you represent later when we discuss about shift, but for now you consider that's how you represent a key point. That representation should be compact and should be very localized. It's not like to represent that you should not be requiring a patch which is spreading across a large portion of your image. So these are the desirable properties that you require for your key points, right? That's what we discussed yesterday. Now, I was mentioning then this Moravec detector has done a very good job. This is something which is a kind of basis for Harris and corner detector. I would discuss about the differences between these two once I finish discussion about Harris corner. Then you will be able to appreciate what the modifications that have been done here, rather than me trying to convey here itself without giving any background to either Moravec or Harris. So that's what we will do. Now, let's go to the Harris corner detector. The idea is this: you would take a patch here. Now you consider a key point for the time being as a small patch around a center pixel, okay, which you considered as a key point. So from all the discussions that we had in the previous class, you might have noticed already that suppose if you have a uniform region, this patch slightly moving in whichever direction you are moving would result in a more or less similar patch, is it not? And suppose you have an edge, aperture problem is there, that's what we have discussed. Let's say I have an edge like this, right? I have an edge like this. Now I have a small patch here, okay, some rectangular patch or a square patch you consider here. So if I have an edge, if I have a vertical edge, if I'm moving horizontally, there is a variation in that patch, okay. But the moment I am moving here across the edge, okay, so there is hardly any difference. So from this, you can make an inference that even a slight movement or change in the position of your patch should result in a large difference in terms of intensities within that patch. Is that statement clear? Because this is what serves for us as the basis for the rest of our derivation for Harris corner detector. For now, for example, in this statement, you ignore about this W of X. I'll come to that a little later. That's a detail. You assume that I have a patch centered at X comma Y pixel. Okay, or all the, in fact, okay, that's again a slight abuse of notation, but that's okay. First, let's get some intuition. So there is a patch here too at a look centered at a certain location. Now, any change in that position, let's call that displacement of that patch we are giving by in the X direction by U and Y direction by V. Now what you would like to do is, for example, let the patch be capital W, okay, that the patch be capital W. You consider all values of xy within that patch, and you subtract from x comma y the new after you move it by a value of u in the x by a value of v in the y direction. You subtract now the corresponding pixels, sum it up over the entire patch, and this is what ideally you want to have maximum value. Let me call that as an energy function or an error function, whatever you want to call it. This is something you want to maximize, and that patch which can efficiently maximize this such that even a small movement of u in the x and v in the direction of y would give you a maximum sum of squared difference. Is that is what you consider as a key point? Is this statement clear to you? What I am doing is, what I am stating here is, even if I move infinitesimally small distance of this patch in by u in the x and v in the y, and then I take difference between these two patches, corresponding pixels in these two patches, subtract them and square them, so that I would, it could be from negative to positive or positive to negative, difference doesn't matter. This is something you want to maximize. A key point you would consider is something in whichever direction you move, this is something which is very high. Is that making sense? It's
So,
not clear
so
to.
what if there are a lot of points that
Hmm.
satisfy this criteria in an image?
Right,
So it
right,
won't be uniquely identifiable in that case,
right.
right?
See, it is not just one key point you want. You want n number of good number of key points you want. So you put a thread just like in the edges, you put a threshold on the edge value, and anything above that you consider as an edge. You will see shortly some demonstrations and illustrations on the images also. You would require some sufficiently good number of these points as well. So what I am saying here is I am considering that the pixels, okay, I am considering an image patch of okay, where I mean xy, for all xy that belongs to this patch w, okay, and the shift I'm giving there, I'm considering it as u comma v. Okay, now how did I define my energy function or error? I leave it to you how you call it. Is I take all pixels, for all pixels x comma y that belongs to this window or patch window, whatever you call it, I don't really care about that, is I x plus u comma y plus v minus of I x comma y whole square. It's just that I moved xy to first I am writing x plus u y plus v. Doesn't matter even if I write the first term as second term as the first term. It's because anyway square is there. Square of sum of squares of differences I am taking there. Doesn't really matter. Another even for small values of shifts here. So these are very small values. Okay. Now when these values are small, can you write x plus u comma y plus v in terms of x comma I of x comma y? What is the kind of who comes to your rescue to write it in terms of x comma y?
Taylor series.
Yeah, of course. Yes, very good. So you tell me now, how do you express it? These are infinite, these are very small displacements from the original position. So how do you write it now? At least first term should be easy to say.
I of x comma y.
Excellent. Very good. Then you know it for 1D for sure. Now you need to tell it for 2D. Thus also somewhere you should have studied it. Any guesswork is also appreciated. Maybe I will write one function. See, this is a function of two variables. Instead of a differential derivative, partial derivative is what you would be getting here. Can you help me now? Multiplied with?
U, sir.
Very good. Second term, you should be able to tell by even not knowing any Taylor series expansion, you should be able to tell by guessing here.
Dou I by dou y into v, sir.
That's all. Yeah, all higher order terms I am not writing here. So let me write it as just an approximation instead of putting equal to. I'll keep it here. Okay. For notational convenience, let me write from now on dou I of x comma y by dou x as simply I subscript x. Similarly, dou I of x comma y by dou y as I subscript y. Okay, that implies my I of x plus u comma y plus v is roughly equivalent to I of x comma y plus I subscript x into u plus I subscript y into v. Okay, now let's substitute this equation here. Then what am I going to get there? E of u comma v is equal to, for all xy that belongs to this window or patch w, what is it that I would get inside now?
IXU plus IYV.
That's all. Okay, so the whole derivation actually in the Harris is based on the matrix representation of this value. But perhaps if you are not very comfortable with the linear algebra and matrix things, you find that difficult to follow. So what I would do here is I would first try to discuss with you in a in a scalar format, and then we will slowly make a graduation into a vector form. That would perhaps would make it easier for you to follow. So let me expand this for now. That would give me ix square times u square plus 2 times ix iy into u comma v plus iy square into v square, right? So this is what e of u comma v, okay, approximately equivalent to, for just convenience I'm writing it as just equal itself, right? So what is the nature of this expression? Just take a look at, maybe if you want, let me write it. So what is exactly going to happen here? Can you just shed some light on how you compute this expression in the first place? Just uh, I want to distribute this summation to each term there, and to that parameter which has nothing to do with the summation, I want to take that out of summation and rewrite that expression. Can you help me with that? How I could write it? Three separate terms where within the summation I just want to keep that variable or parameter that has something to do with that summation variables. Can you help me with that? So I will just keep w here. Okay, you write xy every time, but I'll just keep that w here, ix square times u square plus 2 times over the window. I would do I multiply ix iy for all the pixels within that window and sum them, and outside that I have u comma v. Similarly, here over the window I would take iy, square them up, sum them up, and the whole thing is v square, right? Hope you are able to follow so far. So if you want some interpretation here in terms of the numerical computation, you go to the each pixel within that image, you compute the derivative of it in the x direction. Okay, you already know this forward difference or central difference or backward difference, it's up to you. You compute that ix value for each xy in this window, right? You square it, you sum it across the whole pixels within that window, and then this would become the coefficient of u square. Okay, u and v are the parameters here for small values of moment is what you are considering here. Similar lines here, you compute iy also. For a given pixel, you multiply, don't square ix but multiply ix and iy, and you do it for each pixel, sum them over all pixels within that window. Okay, similarly iy, it's just involved with the derivative in the y direction. Now suppose I consider a constant value for this u of, let us consider a constant value of u and v here. By that, what I mean is, let me call this as a, b, c for the time being. So a u square plus b times uv plus cv square is some constant value. What is the shape of this equation?
Is it an ellipse, sir?
That's right, it's an ellipse, right? It will have the shape of an ellipse, and of course that ellipse could be rotated for certain values. So if it is, you know that x square by a square plus y square by b square equal to 1 would be straight one. Otherwise this buv term, okay, is something that brings a rotation. It's a quadratic form, it's a quadratic equation that has a shape of an ellipse, where this here a constant values, these are all that which you have a constant value would dictate at what distance it is. So the shape that you are going to get here, let me now you make use of this things here. Okay, so it is something that looks like this. You will have one shape here, you consider another value and take the samples of it, and the whole one you can visualize now based on this how it would look like. So to have a faster change, what you should have is these axes, if they are small. Okay, so this is where it has to, if had it been a smaller one, for example, then there is a change here faster from one value to the other. So well, this interpretation from here becomes difficult. On the contrary, if you use a matrix representation for this, you can do a lot of things there. So let me now stop the interpretation of in a scalar mode here, and let me move on to a matrix based representation of it. Again, I am writing this equation now. Okay, so where I would, what is it that I'm going to write here is for all xy that belongs to w. Okay, ix square u square plus 2ix iy times uv plus iy square v square. This is the equation. Okay, for now just see whatever I am writing is making sense or not, and why I am writing like that would become clear shortly for you. So can I write it as, anyway this is a 1 by 1 element. If I consider it, I could write it as 1 cross 2. So that means, let me write here u comma v. There is no need to keep a comma there because this is a matrices. Okay, u comma v. Then let me here write 1 cross 2, then 2 cross 1. 2 cross 1 is, let me write here ix iy. Okay, then again let me write it as 1 cross 2 here. So that would give me ix iy, and then followed by it 2 cross 1. So that means uv. You just multiply them and see what's going to happen here. Okay, I could have started from here, and also I might have written it, but that's okay. See here what is going to happen here. Suppose if I am multiplying these two, right, what do I get? 1 cross 2 with 2 cross 1. Okay, or let me, even better would be to first, you once you write it, you could do commutative property. You write this here, you should be getting 2 cross 2. That would give you ix square. Okay, this and this, then what? Ix iy, and then what? Ix iy. This is iy square. I'm just simply multiplying those matrices. Then I have here, I'm somehow writing every time comma there, uv, and then u comma v. Okay, now this is a 2 cross 2, 2 cross 1, 1 cross 2. Let me, now it's up to you which one you want to multiply. Let's multiply this. Doesn't really matter in which order you do it. Ix square times u. Okay, now I should be getting 2 cross 1, ix square times u plus ix iy times v. Similarly, ix iy times u plus iy square times v. Now you multiply these two. So 1 cross 2, 2 cross 1, 1 cross 1 I would be getting. So that's equal into ix square u square plus ix iy u times v. Well, this is yeah, 2ix iy plus iy square. Okay, you, how do you do 1 cross 2, 2 cross 1? So this you multiply this. So ix square times u square plus ix iy times uv plus ix iy times uv. So I'm just putting 2 here, and this will be Iy square times V. This whole under summation is there. So do you agree that these two are equivalent expressions now? So now I could write it as, in the summation I can take this out, nothing to do with that. So U comma V for all xy that belongs to this window. I have here Ix Iy, right? And then Ix Iy, okay, this whole thing. And of course outside I have here U comma V. Okay, this is one way of writing it, where let's say I could call this as, we were calling it, if you do you remember, we were calling it as gradient of I earlier, dou I by dou x and dou I by dou y, isn't it? Similarly, this is, then I could call it as gradient I whole transpose. So this is one way of representing this UV. Okay, summation for all x comma y that belongs to W, gradient of I, this is a, forget not, this is a vector, this multiplied with gradient of I whole transpose, right? And this then again you are doing with V. And of course this is your U E of U comma V. That's one way. So what it is telling you is, you take the gradients both in x and y directions and you multiply them out. Okay, this, and the outer product of this is nothing but the outer product of gradients. Notice here, for each x and y, you do the outer product and then sum them all over the given window. That is what you are doing it. So you could already sense here that this value to be having a maximum value, it does involve both gradients in x and y directions. How exactly do they involve? We have not yet worked that out. To see that intuition, I am going to write it in a slightly different way again. Okay, this is for giving you an idea that this is in fact is something to do with the gradients and outer product of gradients and sum them all over the window. That is something we are taking a look at here. Now, this I could have written, instead of writing it as gradient, another way is, of course, I just simply expand that and write it. That's all, which would be equal to U UV and then summation over the window. If you just take this one, this 2 cross 1 with this 1 cross 2, you multiply them. So what do I have here? Summation of for each xy, ix square. This is a matrix, so let me put a square bracket there. Ix Iy, Ix Iy, Iy square. Okay, then I have here U and V. Again, similar to what I have written before, UV, then I could have written this as sum of Ix square over the window. Over the window, I compute for each pixel Ix Iy, derivatives I multiply, sum them up. Same here, that would be the second row, first column, and here sum over the window Iy square, right? And then I multiply the resultant one with UV. You could see here 1 cross 2, 2 cross 2, 1 cross 2, 2 cross 1, 1 cross 1 would exactly give me this expression. Okay. And by the way, this is something you would come across in computer vision in a lot of places. and this is referred to as, maybe someone at least might have heard it, this is referred to as second moment matrix. And there is another name which you sometimes rarely used, not so often, but it's another name is called as structure tensor. That's another name for this matrix. Okay, so everything is now there within this matrix. So once you decode this matrix, make some interpretations on how it should be and how it should behave, you are able to get an intuition and clarity about Harris Corner detector.
Sir, how do
Yeah.
we calculate the gradient
Ah,
here?
okay. Okay. That's pretty simple. So how do you compute the gradient? I have a patch here. WW are taking a patch here. Assume that this is your pixel. Okay. So IX is how you do it. For example, this so for all XY. So how are we rating for all XY that belongs to this window? So in this window, for example, you take this pixel. Okay, you start from here. Let's say doesn't really matter ix. If you want to do, you subtract ix, you know this, right? Ix is I of x plus 1 comma y minus I of x comma y. So you do that. This is same as the gradient. This is why we first discussed gradients earlier. This what would give you ix. If you want iy, I of x comma y plus 1 minus I of x comma y. You go to each pixel in your window and then you do these calculations, okay, for each pixel, and this summation is where you would be summing up them over the entire window. On the other hand, here you would be multiplying ix and iy and then summing up over for all pixels. That's what you would do to get these two off diagonal elements. Is that clear?
Yes, sir. So we don't have to use the Sobel kernel or anything like that.
No. And Sobel kernel edge detection is not required. You could, you just actually what you do is you do, I will come back to that also once we discuss, just that I wanted to avoid some basic details. I want to focus on this. I haven't talked about it, but you essentially would do first a Gaussian smoothing, followed by that applying something like this is good enough. Again, I skipped some details. W of xy, I'll come to that a little later once these things are absolutely clear to you. This is the matrix that you have, and now make use of the interpretation that you got in the scalar form, because so visualizing an ellipse in the matrix form is more difficult for many of us, including myself. So that's why we figured out that if you consider a constant value for this matrix, it's going to represent a kind of ellipse. And once you have this in matrix form, you could write it as this. This is a, let's call it as capital M. Okay, let me move to the right slide and then talk about that. Okay, so you all know about, you consider a constant value here. As we have seen the interpretation, let's borrow the interpretation from scalar. If you are not similar to me, is not so convenient in visualizing that this indeed a constant value would represent an ellipse. So let's borrow it from there. Now you have a capital M here, uv multiplied with m multiplied with uv here. This m being constant, okay, would in fact represent an ellipse. And this ellipse, what would be the major axis and minor axis of it? You consider a simple case to begin with, where your m is in this form for the time being. Okay, lambda, there are only, it's a 2 by 2 matrix. So you assume that you have used all the diagonalization approaches and written it as lambda 1 and lambda 2. Okay, assume that now one of them will be minimum and another will be maximum. So they 1 by square root of them, square root of these lambda values, eigen values, would give you the lengths of your major axis and minor axis. So this is and when you are diagonalizing it, suppose you, first case I mentioned is an ellipse, okay, which is like this. In that case, you have ideally these on diagonal, the main diagonal elements to be non-zero and the rest 0. If that is not the case, once you do operations like singular value decomposition, you could write it as R inverse this lambda 1 lambda 2 0 times R, and then this would give you, this operations would be equivalent to transforming your ellipse or rotating your ellipse. Those values are given by this R inverse and R. Nevertheless, once you do that, whatever lambda 1 and lambda 2 you are getting, in them, out of them, if you take the minimum value and 1 by square root of that, of course, and of course you do the same for the other one also, then 1 by square root of lambda min would give you this, and 1 by square root of lambda max will give you not fully one, half of this value, and here also half of this value. In other words, this would give you the direction of the slowest change here, ellipse. So this is a constant value. So I have shown you here, this is how it would look like if you look at the whole stuff there, but that would be the constant value. So if you recollect, for a good point, the moment you make even a small movement from your position, and then you compute the sum of squared difference, that should be maximum. Okay, for that, again, to make intuition, let's look at this in terms of an image where you are calculating. This is your given image. This is the patch you consider W of XY. Now we are considering some discretized values for U and V. U is displacement in terms of X, V is displacement in terms of Y. And what you are plotting here, the black representing 0 value and the white representing the highest E of U comma V you are getting. Now if you look at here, suppose E of 0 comma 0, what does this mean? You are not making any movement. Your displacement in X is 0, your displacement in Y is 0. So obviously when you are then simply subtracting them, okay, here again, now you see the interpretation in terms of here. Okay, now don't go to the Taylor expansion. Exactly here you have to get a comprehensive view, you have to view it from multiple viewpoints. Okay, this is another viewpoint of how E of U comma V would be there. So once you look at it here, it would be 0. Obviously when you move to something like this, there you have maximum value. Okay, here these values are in such a way that around here, even if you are making small shifts here and calculating these values, for the time being, don't worry about W. I'll come to that at later stages, but this is how it is. And what is it desirable is even a small shift in any of the directions should give you the maximum value of E here. In other words, now you make the this is E of U comma V only, you finally managed to write this in this form, and then you diagonalized it. Okay, that's giving you this. And now any small shift should give you high value, means this whole value should be high, or in terms of an ellipse, you should have very small axis there so that it would move to the next value faster. That means this is in the denominator 1 by square root. So your eigenvalues of this matrix should be very high. Okay, all this gymnastics we have been doing by writing into the matrix form, looking at what is the shape of it, to come to the final inference or conclusion that if the summation matrix has large eigenvalues, both of them being large, if even one is large and another is small, there is a leaking at the other end. So even if you are moving, it's like an itch. Okay, if you are moving around that, it's not going to do well. So you should have these two eigenvalues to be large and roughly equal. So it is in order to give you that interpretation in terms of these eigenvalues, we are doing all this rewriting and looking at from different perspectives. Is this point clear? So do you agree that if this M is constant, if the, so see, M you interpret it in this way. Okay, so once you are UV and M, if you are doing it, it's roughly the shape of the ellipse. That so far it is clear, right?
Yes, sir.
Right, very good. And after that, what we are saying is, suppose when you write it in this way, this matrix, eigenvalues of this matrix would tell you the information about what is the length of your major axis and length of your minor axis. And you might not get it nicely in this on diagonal form where off diagonal elements are 0. You might have to use SVD to write this M. And in that case, the matrix R inverse, this diagonal matrix into R is what you are going to get in that case. And this would tell you how much your ellipse is rotating. That's all it has an impact, but still it is an ellipse. Okay. Why it is an ellipse? Better we have seen it in the scalar, because seeing it from a vector matrix representation is difficult. So what all, if this point is clear to you, that this matrix M would represent, for a constant value of E of u comma v, this would represent an ellipse and whose major and minor axis are related to the two eigenvalues of this 2 by 2 matrix. Right. So now what we are saying is, see the direction you could see here, this is constant here. From here, from the constant value you want to move to the another value. If your length of this axis is too large, okay, then it takes, you have to move a large distance there. So that's why you should have these lengths as small as possible. In other words, if that interpretation is not coming out clearly to you, take a look at here while writing it as a scalar quantity. Okay, so this should be large, in other words. So that would in turn will have an impact that this M should be large, which again means that this could be returned as a diagonal matrix with a rotational matrix there. So these eigenvalues, okay, when you have a diagonal matrix, the diagonal elements themselves are the eigenvalues. And so when those values are large, that is when this value will be large and E of u comma v will be large. This length is 1 by square root of lambda 1. This is equal to 1 by square root of lambda. And lambda 1 and lambda 2 being equal, then I have a circle. Then rotation also doesn't really mean anything there.
Yes, sir.
That is fine. That is an ideal scenario. See, in an image, it need not be like that. Even if that is not the case, as long as I move in some direction, even a small infinitesimal thing, there could be a slight variation. I would say lambda 1 should be roughly equivalent to lambda 2. In practice, that is good enough. They need not be, they should be of similar magnitude.
Then only the rotation will make sense.
Right. Not
Right.
the rotation.
Orientation.
Then yeah, and lambda and plus lambda 1 and lambda 2 should be large. They should be large, because if when they are large, this length would be small. 1 by square root of lambda you have. Now consider, this is what you would be, you can infer from lambda 1 and lambda 2 values. Suppose if lambda 1 is very high, how can I make an interpretation for that? Look at here. Suppose I have a very high values for Ix overall, okay? Then Iy values are small. What would happen then? This would eventually result in this having a very high value. Okay, this again not just for one pixel. Okay, remember that there will be a summation here for all pixels which are there within that window. Okay, so then that will have this lambda 2 will become small there. Okay, this lambda 1 would be large, but lambda 2 would become small when you have the gradients in the x direction but not in the y direction, and vice versa. So this would result in one kind of edges, large values, let's say, so gradient vertical edge, you may call it, because it's Ix is horizontal. So just, I'm not, you double check my statement there. If not, it would be the contrary, where lambda 1 is very much larger than lambda 2. And then this region, if you, what you are going to plot here is, I am taking on x-axis lambda 1, pay full attention here, on y-axis lambda 2. These are the eigenvalues that I am getting. If both are small, okay, if that means what is happening here is there are hardly any gradients. So this Ix and Iy, you hardly have any values. So that would essentially represent a flat region when both your lambda 1 and lambda 2 are small. So this is your lambda 1, this is your lambda 2. Now lambda 1 is large, but lambda 2 is not so large. That would be, in a way, edge could be a vertical edge there. Okay, that's something it could result in. And similarly, lambda 2 is very much larger than lambda 1. So then this would be a horizontal edge representing. And when you have both lambda 1 and lambda 2 large, and lambda 1 is roughly equivalent to lambda 2, then your energy function E would increase in all the directions, and those are the corner points you are interested in. See how nicely this linear algebra, matrices, and everything helped us to interpret the cornerness, or having a corner versus an edge versus a flat region in terms of the eigenvalues of the second moment matrix. What it turned out to be here is, if your eigenvalues of your second moment matrix, if both the eigenvalues are large as well as having a similar magnitude, that is what, then E is going to increase in all directions. That's what we wanted as the desirable property for a key point, and that's what would represent corner. Again, don't try to make the representation of corner separate from any key point as such. Okay, for now we are using it interchangeably. So this is what we have arrived at, is that you are given an image, you are given a patch, and the center pixel of that patch, whether you want to consider it as a key point or not, you simply compute second moment matrix for that patch, okay, which is sum of ix square. Okay, this is what, if you want, you compute ix, okay, you compute for that patch iy, okay, and take square of that, you take multiply ix and iy, this you compute the eigenvalues for it, you get lambda 1 and lambda 2 eigenvalues. If both of them are large and somewhat of similar magnitude, okay, this is again relative term, don't worry about more absolute values there, then your E is going to increase in all directions. And now just by simply calculating this matrix and looking at the eigenvalues, you would be able to say whether it's a good key point or not. Well, calculation of eigenvalues. Imagine an image of 256 by 256 or 512 by 512. Now you need to take these patches at each pixel location. You need to do the square sum, and you need to calculate the second moment matrix, and then calculation of eigenvalues. So it doesn't even compute the eigenvalues explicitly, but makes an see, all you need to know here is the relative relationship between the eigenvalues is all you need to know. So can we do without actually computing them? This is also another contribution of Harris corner detection paper, where they avoid explicit computation of these eigenvalues. So how do they do that? Well, they defined a metric here, which is now known as Harris corner response function. Perhaps in their paper, they might have referred it to just a corner response function. Now that this has become quite popular, there are other response functions that were proposed after this work, okay, which we would see a couple of them. Because of that, this is referred to as Harris corner response function, which is defined as you are going to compute the matrix M is there, 2 by 2 matrix is there. You would like to compute the response function R is defined as determinant of this matrix minus alpha times trace of this matrix whole square. So now those of you who still remember, okay, the uh, linear algebra and matrices, determinant of M is nothing but lambda 1 lambda 2. And what is this determinant? If you are given a 2 by 2 matrix, which is, let's say, A, B, C, D, what is the determinant value?
AD minus BC.
AD minus BC, that's all. And alpha minus alpha times a trace. How do you now for the same A, B, C, D, what is the trace of that matrix?
A plus D.
That's all, A plus D, correct. So for this, I don't, to compute this R value, I don't have to explicitly compute lambda 1 and lambda 2. Look at now how you could interpret between this lambda 1, lambda 2 relative values. When, see, for example, in this is again an approximation, okay. This will not be, sometimes there could be scenarios where this could slightly fail and you will go plus or minus from the actual values of that, but that doesn't really matter as long as the overall job done is good. So now look at this. The value taken for alpha is 0.04 times to 0.06 times. This is something they will take, which is empirically fixed after doing some empirical experiments. That case, if lambda 1 and lambda 2 are small, what you would do here is you are multiplying a small value with a small value, you are summing them up, and this again is very small fraction of it, okay. 4% of that value are taking, so it doesn't really matter. This you could somehow ignore it, and this value would be very small. When both lambda 1 and lambda 2 are small, you could clearly see that this would be small. Depending on this value, it might be slightly positive or negative depending on that. So overall, this magnitude of R is very small. That would represent this flat region. Now take a look at the cases, these two cases where lambda 1 is large and lambda 2 is very small, or vice versa, doesn't really matter. You could see these two variables are interchangeable. You could see here a very small value, right? When you are multiplying it, let's say this is again 0.1, assume that this is 100. So it's like 10% of this value are taking here, okay? You are subtracting that from this value, lambda 1 plus lambda 2, you are taking it. So just take some values, even there you could do some mathematical approximations of that, and you would see that when one of them is very large and another is small, this R value would be negative, and large value negative. This could be negative, but it's very small. But a large negative value is what you would be getting when both lambda 1 and lambda 2 are high. Okay, so let's say this is some 100, you take it, okay. Both are 100, so 100 into this is 100 square, okay. 100 square minus from that, this is, let's say, 200. 4% of 200, when you are subtracting from 100 square, okay, 10,000, you are subtracting that, that would be a very large positive value. So you simply given a matrix with, this is how you are going to infer the relative magnitudes of lambda 1 and lambda 2 by computing this R, and then saying if it is R is very large, you say that's a corner point. R is negative and large value, then you say it an H. The magnitude of R is very small, you say it as a flat region. Okay, so just 3 slides I'll show you quickly and end here. You take a point here, which is kind of a uniform region. This is E of u comma v here, that has been plotted for this particular point, taking this to be 0, 0. You would see here, in whichever direction you move, you have more or less same value. That's what is going to happen. You take this point now, which is across NH. So this here you could see kind of a cradle kind of a stuff where you have a flat region there. So as long as you are moving here, this is the energy function we are plotting here. You could see there, this would remain same constant here. But the moment you move in any other direction, okay, this is u comma v changing x and y. So other than that, if you are moving in other directions, indeed there is a jump here. The last slide for today is this, where you, for example, notice here, I have not, this could be equally true for this corner point also. Let's say you want to consider this point, as one of you were rightly pointing out here, what happens if it is not a corner point? This is referred to, you could think of it as a high textured region. So from there you could see kind of a sharp nail kind of a stuff here. In whichever direction you move here, it would give you a large variation. So this you will get large lambda 1 and lambda 2. Previous case, for example, here lambda 1 is large but lambda 2 will be very small. In the first case, you would be getting both lambda 1 and lambda 2 small. Okay, in the interest of time now, I'll stop here. We'll continue this discussion in the next class.